Jnanam paramam dheyam. Knowledge is supreme.
After all these definitions that we have seen, that is the E curve, F curve and the I curve and the mean residence time, variance and skewness, let us look at the residence time distribution in ideal reactors. So, particularly we will consider two cases. One is plug flow and ideal batch reactor, plug flow and ideal batch reactor, and second one is we will look at the single CSTR case. So, these two we will look at and we will attempt to find out how to get the RTD curves for these two types of ideal reactors. So, let us first consider the plug flow reactor. Let us consider the plug flow reactor. So, what is the property of the plug flow reactor? All atoms or all molecules of the material which is actually entering the reactor will spend exactly the same amount of time before they leave the reactor, which means that all elements or all molecules of the material will have exactly the same residence time. So, same residence time for all fluid elements that is actually entering and leaving the reactor. So, therefore, the RTD function must have the following properties. So, first thing is it must have a spike of infinite height, because all of them will have same residence time. Therefore, they will all leave like a plug. So, therefore, the E curve must have a spike of infinite height, and also it must have 0 width, and not just that, the area under the curve should be equal to 1. The spike will be exactly at the mean residence time, and that is very important, because that is the property which actually captures the nature of the plug flow reactor. So, therefore, the spike will be exactly at t equal to V by V naught, that is equal to tau, which is the space time of the reactor, and because there is no dispersion, the space time of the reactor will also be equal to the mean residence time of the reactor, or in the non-dimensional terms theta equal to t by tau, that is equal to 1. So, therefore, the corresponding E curve, because of these properties of the RTD function for the plug flow reactor, the E curve should simply be represented by the Dirac delta function centered at the space time of the reactor. So, this is the Dirac delta function. That is the Dirac delta function, and it is defined as follows. So, Dirac delta function delta x, that is equal to 0 if x is not equal to 0, and it is equal to infinity when x is exactly equal to 0. And the property of this E curve is actually given by minus infinity to plus infinity, delta x dx should be equal to 1. That is the property of the Dirac delta function. In addition to that, the another important property is by that it satisfies the convolution integral, that is equal to g of tau. So, integral of g x, if g x is some function of x multiplied by the delta function into dx, that is equal to g evaluated at that value of tau itself, where x minus tau is actually equal to 0. That is where the spike is actually present. So, now let us calculate the mean residence time for this RTD curve. So, the mean residence time T m is actually given by integral 0 to infinity t into E of t dt, that is the that is the definition for the mean residence time in terms of the RTD function. So, that is equal to plugging in the E curve for plug flow reactor, we will find that it is 0 to infinity T into delta of T minus tau into dt, and that is nothing but tau itself. So, therefore, the mean residence time is exactly equal to the space time, and this actually one would easily guess, because we said that an important property of the plug flow reactor is that all material that is actually entering the reactor and leaving the reactor will actually have exactly the same residence time, and that the E curve is actually going to be centered at the space time. So, therefore, the mean residence time must be exactly equal to the space time of the plug flow reactor itself, which one would actually guess, and it is also clearly shown by the RTD function also. So, now let us look at the second moment, that is the variance of the distribution. So, that is given by 0 to infinity T minus T m the whole square into E of t into dt. So, that is equal to T m square into delta function into dt. And so, now we open up this the T minus T m whole square, and then if one integrates, we will find that this essentially reduces to T square into delta of T minus tau into dt 0 to infinity plus integral 0 to infinity T m square delta of x minus tau dt minus 2 integral t into T m into delta of x minus tau dt. And that is essentially, so the first term here, because of the property of the delta function, is it will simply be equal to tau square, and the second property will simply be equal to plus T m square. So, that will be the second one, and the third one will simply be 2 into t into T m, t into delta function integral T m is constant. So, that will come out of the integral, and t into the delta function will essentially be equal to the mean residence time. So, that will be equal to 2 T m square, and that is equal to 0, because the mean residence time and the space time are exactly equal. So, therefore, the variance is actually equal to 0, and that reflects the property of the RTD function that actually we intuitively guessed. That is, there has to be a spike at exactly t equal to tau with an area under the curve is equal to 1, and the height of the spike is equal to infinity, which means that the variance should be equal to 0 for the distribution. So, let us look at the F curve for the plug flow reactor. So, for a plug flow reactor, the F curve f of t is essentially given by 0 to t E of t by dt, that is by definition, and so that is equal to integral 0 to t delta of t minus tau dt, that is equal to 1 but we know that this integral is equal to 1, and therefore, the f of t curve is nothing but 1, and so as a result so the properties or the RTD function for the plug flow reactor is essentially given by E of t, to summarize, is equal to delta function of t minus tau. So, that is the summary for plug flow reactor. Where the residence time distribution function is essentially given by delta t minus tau, and the mean residence time is equal to the space time of the reactor, which is the volume divided by the volumetric flow rate, and the sigma square is essentially 0, the variance is actually 0, and the F t is essentially equal to 1. So, therefore, if we actually attempt to sketch the E curve and the F curve, we will find that, so that is time, and suppose if this is tau here, at t equal to 0, if there is a spike tracer that is actually put into the plug flow reactor. So, if that is the spike, then exactly after a delay of tau time, which is the space time of the plug flow reactor, the tracer will actually come out, and the same quantity of tracer will actually come out of the reactor. So, that is the outstream, and the height will be infinity. Okay. Now, suppose if I look at the F curve, so this is the E curve, and suppose if I look at the F curve of the reactor, suppose if I look at the F curve of the reactor, then exactly at tau equal to exactly at t equal to tau, that is the space time or the mean residence time of the plug flow reactor, the f value will be exactly equal to 1. So, that is the E curve and the F curve for a plug flow reactor. Now, let us look at the CSTR case. What is the RTD function for a single CSTR? Now, suppose if here is a CSTR and there is this is the inlet stream and this is the outlet stream of the CSTR, and the CSTR is well mixed, and it is assumed that it is an ideal CSTR, and therefore, it is a completely well mixed system. And let us now because it is completely well mixed system, the concentration of the species which inside the reactor should be equal to the concentration of the species in the effluent stream as well. So, which means that the outlet concentration is equal to the concentration of the species in the reactor. And let us now write a material balance on an inert tracer. Suppose there is an inert tracer which is actually fed into the reactor. So, let us say that an inert tracer is fed into the reactor, and if the concentration of the inert tracer is actually C naught at t equal to 0. So, at time t equal to 0, some C naught quantity of tracer is actually fed into the reactor, and now we can write a material balance in order to find out what is the RTD function. So, for any time greater than 0, whatever fluid is actually, whatever tracer is entering the reactor, that should minus whatever is actually leaving, that should be equal to the accumulation of the tracer inside the reactor. Now, if you assume that it is a pulse tracer, if it is actually a pulse tracer, which means that the time at which the tracer is actually fed into the CST is exactly t equal to 0, and nothing before and nothing after t equal to 0. So, therefore, at any time greater than 0, no tracer is actually entering the reactor. So, therefore, the inlet is 0 minus what leaves is the volumetric flow rate V of the effluent stream multiplied by the concentration of the tracer C, and that should be equal to V into dC by dt, which is the accumulation of the tracer in the CSTR. Now, because the concentration of the species inside the reactor is equal to the concentration at which the species is actually leaving the reactor, the C here essentially represents the outlet concentration of the species from the reactor. Reflects the concentration of the species with which it actually leaves the reactor in the effluent stream. So, now one can actually integrate this expression to find out that C of t is equal to C naught into exponential of minus t by tau, where t C naught is the initial tracer concentration, initial pulse tracer concentration of the initial tracer that is actually fed as a pulse tracer, and from this we can find out that E of t is given by C t divided by integral 0 to infinity C of t dt. So, now we know the expression for C t, the dependence of C on time and other properties. So, we can plug that in here, we will see that it is exponential of minus t by tau divided by integral 0 to infinity minus t by tau. So, performing the integration, we will find that because C naught is constant, one can actually cancel out C naught from the numerator and denominator, and so we will find that this will be equal to 1 by tau into exponential of minus t by tau. So, that will be the residence time distribution function for a single CSTR. Now, in terms of the dimensionless, in terms of the normalized RTD function, E of theta is essentially given by exponential of minus theta, where theta is actually t by tau, and E of theta is nothing but tau into E of t. So, that is the normalized residence time distribution function, and now we can actually find out what is the F curve. So, F of theta is nothing but integral 0 to theta E theta into d theta, that is actually 1 minus exponential of minus theta. So, that is the f curve, that is the expression for f curve, which is 1 minus exponential of minus theta, where theta is t by tau and tau is the space time of the reactor, where tau is nothing but v by v naught, that is the space time of the reactor. So, let us attempt to sketch the E curve and the f curve. So, the E curve, so the normalized RTD function, so the E curve essentially looks like this, it is an exponential decay, and then the corresponding f curve is actually looks like this. So, this is 1 and this is theta. So, it actually essentially looks like this, and so the mean can actually be estimated as T m, that is equal to integral 0 to infinity. These are different properties of the distribution, t into E of t dt, that should be equal to integral 0 to infinity t by tau into exponential of minus t by tau, and that should be equal to tau. So, that is exactly what we observed before. If there is no dispersion, then irrespective of whatever is the RTD, then the mean distribution time should be equal to the space time of the reactor itself. And now, the variance sigma square is given by 0 to infinity t minus T m square into E of t dt, and that should be equal to tau square integral 0 to infinity x minus 1 the whole square into exponential of minus x dx. So, where the change of variable is done by setting x equal to t by alpha, and so integrating this is a standard expression. So, while integrating this expression, one can find that is equal to tau square, which means that the standard deviation of the distribution is actually equal to the space time of the reactor itself. So, for a single CSTR, the mean residence time is equal to the space time of the reactor, and the standard deviation of the residence time function is also equal to the mean residence time of the reactor itself. So, now if we compare the various compare the RTD function and the various properties of CSTR, we can find that. So, suppose if we make a comparison, we can summarize the function and the properties that we have found so far for a plug flow reactor and a CSTR. So, the residence time distribution function E of t is essentially the delta function for a plug flow reactor, which means that there is just a delay, and whatever is fed into the reactor is going to come out of the reactor exactly after a certain delay, and the delay is given by the space time of the reactor. And here delta x is actually defined as 0 for x not equal to 0 and infinity for x equal to 0. And the corresponding RTD function for CSTR is 1 by tau exponential of minus t by tau, where tau is given by the v by v. Tau is the space time, which is given by the volume of the reactor divided by the corresponding volumetric flow rate. And then the mean residence time for a plug flow reactor is given by tau, and it is the same for the CSTR because there is no dispersion, and so the mean residence time should be equal to the space time of the reactor itself. And the variance for a plug flow reactor is 0, while for a CSTR it is actually equal to the square of space time of the reactor itself. And then the F curve, it actually is 1 for a plug flow reactor, and it is 1 minus exponential of minus t by tau for a CSTR. So, that summarizes the various properties of the RTD, that summarizes the RTD function and the various properties of the function for the plug flow reactor and a CSTR. So, next let us look at the another reactor, laminar flow reactor. Let us try to estimate the RTD function for the laminar flow reactor LFR, will be referred to as LFR hereafter. So, suppose if there is a tank and there is a fluid stream which is actually entering at 0 and leaving at L. So, that is the length of the reactor, that is L, and the fluid is actually entering under laminar conditions, and it is expected that there will be a parabolic velocity profile. There will be a parabolic velocity profile with maximum at the center and 0 near the walls, maximum at the center and 0 near the walls. So, suppose if the center of the reactor is, so if that is the center of the reactor and that is r equal to 0. So, if I label this coordinates as r, this coordinates as r, and at r equal to 0 it will be maximum velocity, and at r equal to r, which is the periphery, the velocity will be 0. So, that is a parabolic velocity profile. That is the parabolic velocity with which the velocity profile with which the fluid is actually flowing through the reactor. Now, clearly this suggests that the fluid particles, which are actually fluid elements which are actually at the center, they will actually have the shortest residence time because they have the maximum velocity, and so they will leave the reactor much faster than the other fluid elements which are actually present in other radial locations other than 0. So, now, therefore, the velocity profile u is actually given by u max, which is the maximum velocity at the center multiplied by 1 minus r by r the whole square. Now, often this maximum velocity may not be known. So, instead what may be known is the average velocity, that is the velocity of the fluid stream averaged across the whole cross section, and that can actually be estimated from the velocity profile, from the local velocity expression. So, u average, which is the average velocity at a given cross section, is given by volumetric flow rate divided by the area of the reactor at that cross section, and that is given by 1 by pi r square into integral 0 to r u max into 1 minus r by r the whole square into 2 pi r dr. So, here I have assumed that if this is the cross section of the reactor, if that is the cross section of the reactor, then let us assume that there is a small element which is present here from the center, and that is located at a distance r, and the thickness of this is actually dr. So, therefore, the volumetric flow rate of the fluid and at any cross section is given by the local velocity multiplied by 2 pi r dr into integrated over the whole integrated between 0 and r. So, that gives the volumetric flow rate at that cross section, and pi r square is the corresponding area at that cross section. So, from this integrating this expression, we will find that will be equal to u max by pi r square multiplied by 2 pi r square by 2 minus 2 pi by r square into r power 4 by 4 and the limits are 0 to r, and that is equal to u max by 2. So, the maximum velocity is simply twice the average velocity, that is the averaged over the cross section of the reactor, and in fact, the average velocity is also called as the cup mixing average, and so u max is equal to 2 times u average. So, substituting this in the expression for the velocity, we can actually rewrite the velocity expression as u equal to 2 times u average multiplied by 1 minus r by r the whole square, and that is equal to 2 v naught by pi r square. V naught is the volumetric flow rate with which the fluid is actually flowing at that cross section into 1 minus r by r the whole square. So, that is the expression for the velocity with which the fluid is actually flowing as a function of the radial position. Now, we can now estimate what is the time that is actually spent by the fluid particles at that is entering at a given location r. So, that is actually given by the length of the reactor L divided by the velocity with which the fluid is actually flowing in that radial location r, which is actually u r, and that is given by pi r square by v naught into L into 1 by 2 times 1 minus r by r the whole square. So, that is the time that is taken by different fluid elements that is actually entering the reactor at any r location. Okay. So, that is actually equal to tau divided by 2 into 1 minus r by r the whole square, where tau is given, tau is the space time of the reactor, which is given by V divided by V naught. So, now we need to relate the, we need to now relate what is the what is the, we need to find out what is the RTD function E t. So, in order to find that, we need to know what is the fraction of this fluid that is leaving and what is the age of that particular fluid. So, now the volume of the fluid, the volumetric flow rate between r and r plus dr. So, that is the volumetric flow rate of the fluid which is actually flowing between r and r plus dr, and that is given by dV, that is equal to u r into 2 pi r dr. So, that is the volumetric flow rate of the fluid which is actually flowing in this element dr, that is between r and r plus dr. So, now the fraction of the total that is actually flowing through this small element dr is actually given by dV divided by V naught, where V naught is the total volumetric flow rate, dV by V naught gives the fraction of the fluid that is actually flowing through this element dr. So, that is given by u r divided by V naught into 2 pi r dr. So, that is the fraction of the fluid that is actually flowing through this element dr, and in fact, that is nothing but the E of t into dt, because the fraction of the fluid that is actually flowing through this small element dr, and also the fluid which is actually between V and dV, which is spending the time t and t plus delta t, is what is given by this RTD function E of t dt, and that should be equal to dV by V naught, which is actually the fluid which is flowing between V and V plus dV, whose residence time is actually between t and t plus delta t. So, what we have seen so far in this lecture is essentially different properties of the residence time distribution, which is the mean. We have looked at the variance and we looked at the skewness, and then we moved on to the residence time distribution of the ideal reactors. Particularly, we considered the plug flow reactor, and then we found out what is the residence time distribution for this particular reactor and what are the properties of the residence time distribution, and specifically we found out what is the E curve and the F curve as related to the time, as a function of time. And next we looked at the residence time distribution function for a single CSTR. We found the E curve and the F curve and the corresponding properties, and then initiated discussion on the laminar flow reactor. Thank you.